In this lecture, we will discuss about nucleophilic aromatic substitution. If you see an alkyl halide, on alkyl halide we have nucleophilic substitution reaction. But this kind of substitution reaction does not take place on vinylic halide and aryl halide. So nucleophilic substitution reaction does not take place on vinylic halide and aryl halide. This class of halide is called vinylic halide. So if a chlorine is attached or a halide is attached to sp2 carbon, so this is an example of vinylic halide. Aromatic halides are called aryl halides. So this is aryl halide. So in both cases nucleophilic substitution reaction does not take place. This means this reaction will not take place. Similarly, in case of aryl halide, once again this reaction will not take place. So no substitution. What is the reason? First reason is, in both cases carbon halogen bond has some double bond character. So we can write one resonating structure for this molecule. So this carbon halogen bond has a double bond character. Similarly, in case of benzene, that is in case of aryl halide, once again we have a double bond character between carbon and halogen. In this case we can write more resonating structures. So from these resonating structure it is clear that in case of vinylic halide and in case of aryl halide, carbon halogen bond is having some double bond character. So carbon halogen bond has some double bond character. So it resists in both kind of reaction, either we have SN1 or we have SN2. Breaking of carbon hydrogen bond is involved. So now carbon hydrogen bond has a double bond character. So dissociation of carbon hydrogen bond becomes tough. This is one reason nucleophilic substitution reaction does not take place on vinylic halide and aryl halide. Another reason we have, in both cases, let us say case of vinylic halide, we have a pi lobe that is up and perpendicular to this plane and bottom this to perpendicular to this plane. So if this is the plane of alkene, we have electron cloud on the top of this plane and we have electron cloud on the bottom of the plane. So it is not easy for nucleophile to attack on this carbon. So basically this electron cloud prevents nucleophile to attack on the carbon. So SN2 becomes rate for SN2 becomes slower. So chance of SN2 decreases. Chance of SN2 decreases due to electron pair electron. So now this electron cloud can repel this nucleophile due to repulsion between pi electron cloud and nucleophile. Same thing happens in case of benzene. Orbital picture diagram for benzene is something like this. So benzene has pi electron on the top of this plane and pi electron on the bottom of this plane. Let us say we have chlorine here. If a nucleophile wants to attack, this gets repelled by this electron cloud. So once again, chance of SN2 decreases. So due to repulsion between nucleophile and electron cloud, and pi electron cloud, chance of SN2 decreases. SN2 decreases. This can be also said on the basis of a steric factor. In both cases, there is a steric repulsion. This is a big group. Nucleophile cannot attack on this carbon. Similarly here, we have a steric repulsion due to this pi electron cloud. So due to a steric reason, SN2 rate decreases. We also does not have SN1 kind of reaction. So on alkyl aryl halide and vinylic halide, even we does not have SN1 reaction. So no SN1 in this case also. So if you remember, in SN1 we have a carbocation. So first step is breaking of carbon halogen bond. Even though this bond has a double bond character, if we break this bond, we will have a carbocation, and this carbocation is positive charge on sp2 hybridized carbon. Similarly in case of benzene also, If we break this carbon halogen bond, we will have a carbocation that has a positive charge on sp2 carbon, and positive charge on sp2 carbon is less stable because it has more s character. This means more close to nucleus. A positive charge more close to nucleus is less stable. So we can say these two carbocation, vinylic carbocation and arylic carbocation, that is aryl cation carbocation, are less stable. So this prevents SN1 reaction. So we does not have either SN1 or SN2, SN1 or SN2, both are prevented. On alkyl aryl halide and vinylic halide. If electron withdrawing group is attached at ortho or para position or both, chance of nucleophilic attack in benzene ring increases. For example, if I have this aryl halide, in this case if I take a nucleophile NH3 and we require a strong condition, high temperature and heat, so in this case we can remove this Cl and we can add one NH2 group. Similarly, if I have the same compound and this is treated with KOH around 100 degrees centigrade, this also gives substitution product. So we can say if electron withdrawing group is attached to the benzene ring, chance of nucleophilic substitution increases. In case of electron withdrawing group, electron from benzene ring is attracted towards electron withdrawing group. So electrons are attracted to electron withdrawing group and this decreases the concentration of electron inside the ring. So we can say electron withdrawing group decreases electron concentration or we can say decreases the electron cloud density inside the ring. Basically, for nucleophilic aromatic substitution there are two pathways. One path is called addition elimination Another path is called elimination addition. So in this case first happens addition, then happens elimination, but in this case elimination happens first and then happens addition. Elimination addition is finally substitution. So if you eliminate something and you add something, or if you add something and eliminate something, it will finally result to substitution. So in this lecture we discussed that is aryl halide or vinylic halide does not go SN1 or SN2. The reason is repulsion between nucleophile and electron cloud. Another reason is double bond character between carbon chlorine bond. Another reason is a steric reason. Next we said on benzene ring we have nucleophilic substitution reaction if electron withdrawing group is attached at ortho and para position. And finally we said there are two ways to have substitution in benzene ring. One mechanism is called addition elimination, another is called elimination addition.